Okay, welcome back from the weekend. We'll get started today. Um, so, the first thing I want to talk about before we get into the chemistry is just a quick recap of the exam results that we had last week. Um, so here's at the bottom is the distribution, and what you'll see is that our average this semester was 13.3 out of 20. So that is a little bit better than last year. So it's good to see that sort of is actually better than the last 2 years, as you'll see down below for the spring 19 and 18, same sections that I taught. The other thing that's good is that our average was about 1 point higher than the other sections that are running concurrently this semester, which I'm happy about because I'm competitive and I don't like to lose, so thank you for that. But at the same time, I'm sure a lot of you think that there's still room for improvement, so if you want to, if you're not happy with your exam score, there's still plenty of time for you to turn things around. I'm happy to meet with you individually to discuss strategies for that, but I think what it really boils down to is just changing your habits, trying to do as many practice problems as possible, things I've been harping on all semester. Your copy of the notes might have another slide related to homework attempts. That's actually outdated information. I didn't get a chance to update that. So that's from last semester. I suspect that this semester the trend is still true, which shows that the students that do more homework attempts get higher exam grades on average. But I'm not going to talk about that today because I didn't have a chance to update it for this semester. All right, so again, if you still have, there's still like 2 more days to ask for regrades on your exam. So if there's any problems that you don't think were graded correctly, please let me know and I'll fix it. Chances are you're not going to get any points back, but there are a few people that have, so it's not impossible. And like I said, just a couple more days left, though. You do need to do that within 1 week of the exam closing, so that's basically Wednesday evening. All right, so what we're going to do today is we're going to go into Chapter 5, and at this point, the course is going to make a pretty abrupt change. So, we talked about at the beginning of the semester that this is an atoms first approach to general chemistry, meaning that we've talked now in great detail about the structure of the atom, the arrangement of electrons around atoms, the combination of 2 or more atoms to form molecules, and how the electrons arrange themselves in those molecules. So we've done a lot with this, individual atoms, individual molecules. That's kind of what the whole first 4 chapters are about. Now we're going to sort of take a change in this and go and start talking about collections of atoms and molecules at the macroscopic level and how they react with each other, some of the properties of chemical reactions and other things related to that, and also some physical and chemical properties of elements and compounds. So things are going to change a lot, and as you'll see, this part of the course becomes a lot more quantitative, a lot more numerical. So most of the first exam was conceptual questions, not a lot of calculations, not a lot of numbers, just a few questions maybe that had that. From now on, we're going to be doing things, at least for the next 4 chapters, that are primarily going to involve calculations, numbers, very quantitative. So the first thing I want to introduce along those lines is the definition of the atomic mass. So as we'll see, atomic mass is somewhat related to mass number, a concept we've already introduced much earlier on, but there is some differences in the definition and exactly what it means. So the first thing is if we're talking about the mass of an individual atom, the mass unit that we use is called the atomic mass unit, or AMU. And how this is defined is basically we take carbon-12 as our standard. So this sort of assumes that if you have the isotope C12, that the mass of C12 is exactly 12 AMU, 12.000000, however many zeros you want to go. That's the mass of the carbon-12 isotope in AMUs is exactly 12. And so 1 AMU is that mass divided by 12. So basically we're using carbon-12 as our standard for the AMU, the atomic mass unit. And so what that means is that with 12 carbon-12 as our standard, all other atomic masses are relative to this. Okay? Because it is possible, there is technology that exists to measure the relative masses of atoms. It's not particularly easy to measure the absolute mass of an atom, as you might imagine how tiny they are. But we can measure relative masses pretty well. So basically we take carbon-12 as our standard, exactly 12 AMU. 1 AMU is then 1/12 of that mass, and then every other atomic mass is relative to that. So as an example, if we wanted to determine the mass of carbon-13, the other major isotope of carbon, what you would find is that if you did an experiment, the technique, not really important what this is about, but the technique is called mass spectrometry, where you can measure relative masses of different isotopes or different molecules, if we're talking about compounds. And what you do is you would get a relative mass, a ratio of the two masses, which would come out to 1.0836. And then what you'll find then is that the absolute mass of carbon-13 would be this number times the mass of carbon-12. Okay, so we're just basically taking this ratio and then finding out the absolute mass of 13 would be 13.0032 AMU. So what you'll notice then is that the atomic mass is, for a single isotope, is somewhat related to the mass number, because the mass number for carbon-13 is 13, and the atomic mass is 13.0032. Now the question is, why is it not exactly 13, and why are a lot of, most other isotopes not exactly equal to the mass number? Now we're not going to get into a lot of detail on this because this is nuclear chemistry, which is a whole different topic that we don't cover in this course. You'll see a little bit of it at the end of chemistry too. But basically there's this famous equation, E equals mc squared, which says that energy and mass are sort of two equivalent quantities that are related to each other. And what happens is when you form a nucleus, a lot of energy is released when the protons and neutrons come together to form a nucleus. And because energy and mass are related, when you release all that energy in the formation of the nucleus, you also then change the mass of the nucleus. So a lot of energy is released when nuclei are formed. Which changes the mass. And the amount that mass changes by is different for every single atom, every single isotope on the periodic table. So it's not that it changes by the same amount every time. It depends on how many protons and how many neutrons come together and how much energy is released when they come together, which is not something we're going to talk about how to calculate or determine in this class. So that's sort of at a very broad level, the reason is that you're releasing some mass when the nuclei form, and so then the mass number is not typically, the atomic mass is not typically a whole number. Now the other thing that's important is that up here we talked about the masses of individual isotopes, carbon-12 being exactly 12, carbon-13 being close to 13, but typically what we want to talk about is the atomic mass of a naturally occurring sample of the element, not just one isotope, but all the isotopes of that element that are sort of mixed together naturally when you have the element. So to do that, you need to define what's called the percent abundance, which is the relative amount of each isotope in a natural sample of that element. So most elements that exist in the world are going to not be a single isotope, but actually a mixture of two or more isotopes. So what we define as the percent abundance is the relative amount of each isotope in a natural sample of that element. All right, it is possible using separation techniques to get pure isotopes of an element, so to get something that's 100% carbon-12 or 100% carbon-13. But if you just dig carbon out of the ground, it's not going to be just carbon-12 or carbon-13. It's going to be a mixture of the two, and that's true for almost every element. Almost every element has two or more isotopes that make it up naturally. And so as an example, the one that we've been dealing with, which is carbon, most of carbon that occurs naturally is carbon-12. So carbon-12 is going to be 98.89% abundant, but as you recognize, that's not exactly 100%. There's still some left, and that means carbon-13 would be the rest of that 1.11%. If you go out to more and more decimal places, there'll be tiny, tiny amounts of carbon-14 as well. But to an approximation of 2 decimal places, 100% of carbon that occurs naturally is going to be carbon-12, which is most of it, 98.89%, but also a little bit of carbon-13. Okay? So then what that means is if we want to talk about the atomic mass of carbon, which is a mixture of isotopes, or the atomic mass of any element, which is a mixture of isotopes, we can't just know the individual isotope masses. We have to basically find the average of those. And so the precise definition of atomic mass for an element is going to be a weighted average of the isotope masses. So you have to know how many isotopes there are, what their abundance is, and then you can find the weighted average of all of those isotope masses to get the atomic mass for that element. All right? And so the way that we calculate a weighted average is we take the fraction of isotope A, where fraction is just percent divided by 100 out of 1. Fraction of isotope A times its mass. So each isotope has a different mass, as we talked about earlier in the course. And then we're going to add to that the fraction of the second isotope, which I'll call B, times its mass, and so on. All right, so however many isotopes you have in that naturally occurring sample, you're going to take their fractional abundance, multiply it by the mass, and then add all those numbers together. Now, an important point is that you can approximate the isotope masses as the mass number, but as we talked about at the beginning of today, the isotope masses will not be exactly equal to the mass number for that isotope. But an important point, though, is that when you add together all the fractions, the fractional abundances, that should equal 1 or 100%. So however many isotopes you have, the sum of all the fractional abundances is going to be equal to 1, or the sum of the percent abundances will be equal to 100% for that element, of course. All right, so that's kind of the definition of atomic mass. So let's do a couple example problems related to that concept. So if we have boron, the fifth element on the periodic table, boron has 2 isotopes as well, just like carbon does, but their percentages are a little bit more even, I suppose. So about 19.9% of boron is in the boron 10 isotope, which has this individual isotope mass. And then the other 80.1% is 11 boron, which has that atomic mass. All right, so what we're going to do then is, in this problem, we want to determine the atomic mass of boron. So the atomic mass, as we said, is just the weighted average of the isotopes. In this case, there's only 2 isotopes, and the majority of the problems we would give you in homework assignments and tests only have 2 isotopes, but there could be some with more. But you're just going to take the fraction of each isotope, multiply by the mass of that isotope, and you're just going to add all those together, however many you have, in this case just the 2. So we're going to just do those. Remember that fraction is percent divided by 100, so the fraction of the boron 10 isotope is the percentage, which is 19.90, divided by 100. Which is 0.199. If you forget to convert percentages to fractions, you're going to calculate an atomic mass that's 100 times bigger than the isotope masses, and hopefully that would raise a red flag or some sirens in your head or whatever the case is. But we have to make sure we convert to fractions, so we're going to take these percentages and divide them by 100. So similarly, this number, 80.10%, which is the percent abundance of the 11 isotope, we divide that by 100 to get its fraction. And now all we have to do to find atomic mass is just plug in the numbers. So 0.199 is the fractional abundance of the boron 10 isotope, and the mass of that is given as 10.01294 AMU. Again, it's close to the mass number, but not exactly, so if we want you to be very precise with this, we'd have to give you the isotope masses. If we don't give you the isotope masses, assume that they're equal to the mass numbers, 10 and 11, but if we give you actual isotope masses to however many decimal places, it's important that you use all those decimal places to make sure your answer is quantitatively correct. And then the second isotope has a fractional abundance, as we said, of 0.8010. Those two add up to 1, as they should. And then the mass of the second isotope is the 11.00931. I should have put units in. This is AMU. And so what that comes out to numerically is 1.993 plus 8.818 something, and we get maybe not enough decimal places, but 10.811 AMU, right? So that would be the atomic mass of boron. And now maybe the not so great mystery is revealed of what that other number means on the periodic table. So this is the atomic mass of naturally occurring boron, which consists of these 2 isotopes. And if we go to the periodic table, what we'll see is that in addition to the atomic number, which we've been using a lot, each element on the periodic table has a number below it, and you see for boron that number is 10.811, so that's the atomic mass. So the numbers that are below the symbols on the periodic table, those are the atomic masses, which again represent the weighted average of all the isotope masses for that particular element. And as you can see, some of them are pretty close to whole numbers like carbon, but some of them are pretty far away from whole numbers, indicating that you likely have a mixture of 2 or more isotopes in relatively equal amounts, okay? So that's what all those numbers then mean on the periodic table. So they're related to the mass number, but they're not a mass number. They're a weighted average of all the isotope masses. So it's, again, a little bit of a distinction there. All right, so that's the first sample problem. The other one that's going to be common for you to do is to solve for an unknown abundance. All right, so in this problem here, if you go to the periodic table, or it's stated right here, you'll see that chlorine has an atomic mass of 35.45, and it has two naturally occurring isotopes, which are 35 chlorine, the isotope mass being a little bit less than 35, and then 37 chlorine, the isotope mass being a little bit less than 37. And we want to know what is the percent abundance of the lighter 35 isotope. So in this problem here, we're dealing with atomic mass, we're dealing with individual isotope masses, we should use that relationship that we used in the previous problem. But here we're working a little bit backwards because we're not giving you the fractional abundances. That's our unknown in this case. And it turns out we actually have two unknowns because we don't know the abundance of either isotope. So what I'm going to do is I'm going to call the fractional abundance of 35 chlorine, the lighter isotope, I'll call that X. So whenever you have two unknowns, it's conventional, of course, to call them X and Y. And the fractional abundance of 37 Cl is equal to Y. So those are our two unknowns. And then if we have two unknowns, we need to put together two equations that relate these unknowns. So the first one we're going to do is the definition of atomic mass. So we remember the relationship we used in the previous problem is that the atomic mass, which is given here as 35.45, is equal to the weighted average of the isotope masses. And so that's going to be the fraction of each isotope multiplied by its mass. So the fraction of the 35 isotope we called X, and we're going to multiply that by its mass, which is 34.96885. Sorry, yeah, that's right. And then the fraction of 37 isotope is Y, and that's going to be multiplied by its atomic mass of 36.96590. And so this is the definition of atomic mass. The atomic mass of chlorine, which is given as 35.45, is equal to the fraction of the first isotope times its mass plus the fraction of the second isotope times its mass. Now the other relationship, remember, is that however many fractional abundances we have, however many isotopes we have, the sum of their fractional abundances should equal 1, or 100%. And so what that means is that our second equation is that X plus Y, the sum of the fractional abundances, should equal 1. Okay? So now we have two equations, two unknowns, and algebra is a prerequisite for this course, so we should all know how to deal with this. And so what that means is that if we rearrange Y is equal to 1 minus X, we're going to solve for X. We're looking for the abundance of 35 Cl, which is X. We could in principle solve for X or Y, but X gets us there more directly. So we're going to take this 1 minus X, and we're going to replace that Y with 1 minus X, okay? So then we're going to get an equation that looks like this. 35.45 is equal to 34.96885 X plus 36.96590 times 1 minus X, replacing the Y with 1 minus X. And then I'm not going to go through the rest of the algebra, but what we should end up with is that X is equal to 0.7590. That's the fractional abundance. The percent abundance is just going to be this number times 100, which is 75.90%. All right? So that answer would be choice C here. So basically, chlorine has two isotopes that occur in approximately 3-to-1 ratio, 75% for chlorine 35, and then about 25% for chlorine 37. All right, so that's how we would deal with those. So again, two problems on this topic. You could see either one. There's really just one relationship, though, that's important, which is the definition of atomic mass as it relates to the isotope masses. So any questions on this topic before I move on? Yes, go ahead. Shout it out.
We're assuming that X plus Y is equal to 1 because we're assuming this makes up 100% of all isotopes, right?
Yeah, because we're telling you in the problem that it's two naturally occurring isotopes. So we're telling you that it only has two isotopes. For this type of problem, we couldn't really give you more than two. We're not going to ask you to solve problems with 3 unknowns. That would be hairy and probably not possible with this information. So in these types of problems, where you're solving for an isotope abundance, it's going to be just 2 isotopes that you're dealing with. In problems like this, where you're calculating the atomic mass, we could in principle give you more than 2 isotopes, but they would all be listed in the problem, so it's right there for you. You don't have to wonder how many there are. All right, any other questions? All right, so the next thing we're going to talk about is a very important concept in chemistry called the mole. This is probably going to be the most important concept for the next few chapters of this course, especially these next two. And so let's define what a mole is, and then we're going to see how that relates to atomic mass as we circle back to it. So what we cover now is not just going to be thrown aside. We are going to relate that to the mole here in a little bit. But first, let's define the mole in more general terms. So the important thing to realize about the mole is that it's just a counting word. So there's not too many of these in everyday English language, but you're probably familiar with some of them. So if you have a dozen of something, how many is that? Does anybody know what a gross is? Close, but not quite. So it's related to the dozen, but how many dozen is a gross? Yeah, a gross is 12 dozen, so that'd be 144. And then a score, does anybody know what a score is? Abraham Lincoln, 7 years ago, what did that score mean? 20, yes, so score is 20. Now again, we don't use these words a whole lot in most of our everyday language, except for dozen's pretty common, I suppose, especially if you frequent the bakery or the grocery store. But those are counting words, dozen, gross, score. There's probably other ones that I don't list here. And the mole is also a counting word. So the question is, how many things are in a mole? If there's 12 things in a dozen, if there's 144 things in a gross, and there's 20 things in a score, how many are in a mole? It's that special number that you're probably likely familiar with, 6.022 times 10 to the 23rd. And we can use the mole to count anything. There are 6.022 times 10 to the 23rd things in a mole. It doesn't matter what we're counting. Now, of course, in the context of chemistry, we're usually going to be counting atoms and molecules when we talk about moles, things that are very tiny. We're not going to count people or apples or eggs in terms of moles, because there's probably not that many on the whole planet. Well, certainly not that many people, probably not that many apples or eggs on the entire planet either. But we use it for things like atoms, which are very tiny, and where a mole would then represent a reasonable amount of that substance. And this number here is referred to as Avogadro's number. Now, I believe the story goes that Avogadro didn't actually come up with this number. Somebody else did, and they had a man crush on Avogadro, so they named it after him. Avogadro made some other important discoveries that we'll cover a little bit later on. The number's named after him, but I don't think he was the one that actually discovered it, as the story goes, but I'm not sure if that's true or not, but that's what I've heard. So let's do a little fun sort of thought experiment to understand just how big of a number the mole is. So 6.022 times 10 to the 23rd. Hopefully that strikes you as a large number, one larger than you've likely counted to in your life, but how big is it exactly? So let's say that we wanted to take a mole of M&Ms and stack them over the entire United States of America. Now, I'm not going to go through this calculation in detail, but basically what I did to come up with this final result that I'll give you here in a little bit is let's assume that the volume of one M&M is about 1 cubic centimeter. So that's maybe not exactly correct, but it's close enough. And then some other things we'll need to do this calculation. So basically we're trying to figure out, if we want to stack 1 mole of M&Ms on the United States, how many layers of M&Ms are we going to have before we run out of our 1 mole of M&Ms, okay? So the volume of one M&M is a cubic centimeter. The area of the United States in a different unit, but we could convert if we needed to, is 3.02 times 10 to the 6th square miles, which we'd have to probably convert to some units like centimeters. Then what you would come up with, if you're covering the United States with a mole of M&Ms and you're stacking them until you run out, anybody have a guess, how high would your stack of M&Ms be? 2 what? 2 stacks? 2 layers? 2 inches? 2 feet? 2 miles? You're actually not too far off. The real answer is 50 miles. Now hopefully that makes you realize how big a mole is. So if we were to stack M&Ms over the entire United States of America and we just had 1 mole of M&Ms, our stack would be 50 miles high by the time we're done. So that is an absurd number of things, right? Or if we want to put it in terms of the number of layers, that's 8 million layers. So we have to cover the United States 8 million times with M&Ms to run out of our mole. All right, so clearly it's a huge number, and that's why we only use the mole to measure very tiny things, because it's not very practical for anything else. All right, well, here's another one that's fun to think about. So how many teaspoons of water are there in all of the world's oceans? So let's say we were going to scoop out all the water from the entire Earth that's in the oceans and use a teaspoon to do it one at a time. So we can figure that out too. The volume of the oceans is, again, I'm giving you all kinds of different units here, and I'm not converting them, so I'm not going to you're going to have to do this on your own if you want to really know how to get these results, but it's about 1.3 times 10 to the 9th cubic kilometers. And what that works out to then, if we convert that into teaspoons, is about 2.65 times 10 to the 23rd teaspoons. So that's close to 1 mole. Not quite a mole, I suppose, but close. So basically, there's 1 mole of teaspoons of water in the entire world. So if you were to take all the water in the world in the oceans and scoop it out, you'd have to do that Avogadro's number times to get all the water out. Or another fun way to think about it is that there's more molecules, I think there's more molecules of water in 1 teaspoon than there are teaspoons of water in the entire world, in all the oceans. So again, further underscoring how big the mole is as a number and how tiny molecules are when we're counting them using that number. So that's hopefully slightly mind-blowing information to understand how big the mole is. Now, of course, how big the mole is not going to really matter for us too much as long as we know how to use it. And so another relationship that involves the mole that's going to be very important for us is that if we talk about the atomic mass in AMU, sorry, still getting over this crap. All right, so we talked about the atomic mass in AMU. That's sort of, if you're thinking about the mass of an individual atom or molecule, that's kind of the mass unit we use. But another alternative or interpretation of atomic mass is that the atomic mass represents the mass in grams of 1 mole of an element. All right, so we said that the atomic mass of carbon was right about 12. And so that means if you have 12 grams of carbon, that represents 1 mole of carbon. In every element, this relationship is true. The mass of 1 mole of that element is equal to its atomic mass. And so, one of the heaviest naturally occurring elements is lead, which has a mass of about 208, I think. So the mass of 1 mole of lead would be 208 grams versus the mass of 1 mole of hydrogen would be 1 gram. So there's quite a wide range of molar mass, atomic masses available. But in any case, whatever that atomic mass is represents 1 mole of the element, meaning that represents 1 mole of atoms of that element, 6.02 times 10 to the 23rd atoms of that element. So with the definition of the mole, and with the alternative interpretation of the atomic mass I just gave you, we now have 2 conversion factors involving moles. Basically what we're going to be doing for all of chapter 5 and 6 is building up more and more relationships, more and more conversion factors that involve the mole. Because as we'll see, the mole is sort of the key quantity when we're talking about chemical reactions. So the 2 that we now have are that there are 6.022 times 10 to the 23rd atoms or molecules or things, whatever makes up that substance, in 1 mole. So it depends on what the substance is made of. If you have an element, there's going to be 6.022 times 10 to the 23rd atoms in 1 mole. If you have a compound that's made up of molecules like water, there would be 6.022 times 10 to the 23rd molecules in 1 mole. So it's basically 6.022 times 10 to the 23rd of whatever makes up that substance in 1 mole. So that's one relationship, and of course we can invert that ratio and do 1 mole over 6.022 times 10 to the 23rd. Those are both equivalent quantities and both unit conversion factors. And then the other one that involves mass is that the atomic mass of an element in grams also can be written as per 1 mole. So we can convert between mass and moles using atomic mass for an element. Now, in terms of practicality, this one up here, the definition of the mole, is important to know, and it's sort of how we first introduced the mole. It's not something you're going to really use a lot in the chemistry lab. We don't go into the chemistry lab and count out 6.022 times 10 to the 23rd atoms of something and measure it that way. The relationship involving the mass is much more commonly used. So if you want to figure out if I need 1 mole of oxygen for an experiment, often the way I'll do that is by measuring out the correct mass of that element for 1 mole. Not so much counting atoms and molecules, but that is an important definition that we're going to use. So what we're going to do now is just go through several sample problems involving these relationships to see how they're used. So the first couple are just going to be 1-step conversions. So again, we're going to use dimensional analysis to do this. We have a quantity in 1 unit, and we want to convert it into an equivalent quantity in a different unit, and so we're going to use the appropriate conversion factor that links those 2 units to each other. So in this one here, if we have a helium cylinder, which people like to waste on balloons, but it has much more important purposes that we should save it for, to be honest. That's neither here nor there. But anyway, a cylinder of helium contains 239 moles of helium, so we want to know how many helium atoms are in the cylinder. And so anytime we're asked about how many atoms or molecules, we should automatically think of Avogadro's number. We're given the moles here. So the way we want to set up these problems, which are going to be increasingly more and more complex as we go through, is we want to write down what we're looking for. We're looking for the number of helium atoms. And we're going to then do a series, however many conversions we need to get that, starting with what we know. And what we know is that we have 239 moles of helium. So that's going to be our starting point. So we start with a quantity where we know how much we have in that particular unit. One thing I don't think I mentioned yet, or maybe I did earlier, but the abbreviation for moles is just MOL. It's a pretty lame abbreviation because you just take off one letter, but that's going to what we're going to use, just MOL for mole. So we have 239 moles of helium. And like we said, our goal is to figure out how many helium atoms there are, so we need to find the conversion factor that links that. And so to make sure we write it in the correct way, we want to convert into number of helium atoms, and we want moles of helium to cancel out. So we're going to do it again, dimensional analysis to figure out that we want moles of helium on the bottom, number of helium atoms on the top, and the relationship that links those two is Avogadro's number, 6.022 times 10 to the 23rd helium atoms per 1 mole of helium. And so moles of helium cancels out. That gets us into number of helium atoms, which is 1.44 times 10 to the 26th helium atoms. All right, and again, if you're counting individual atoms and molecules, it typically is going to be a very large number. All right, so what you'll notice in this problem too is that I told you it was helium, but is the fact that it was helium, did that really come into play at all in how we did the problem? So when you're using Avogadro's number, when you're counting atoms and molecules, the identity of the substance doesn't matter. Now, of course, what the fundamental particle is for that substance will change. So this is an element, so it's going to be made up of atoms. If we were talking about a compound, it would be made up of molecules and so on. But when you're counting atoms and molecules, you don't need to worry about what the identity of that substance is. You're just going to use Avogadro's number directly. And there's no change. No matter what the substance is, you're going to just do that the same way. So when you're counting atoms and molecules, if we want to know how many atoms or molecules are in the sample, you should automatically think of Avogadro's number, and you're just going to use it with the identity of the substance not mattering in that case. Okay, so that's how we use Avogadro's number in just a single one-step conversion to go from number of moles to number of atoms. All right, this next one here also has one step, but we're going to be with a different starting point. So one of my favorite elements is gold, not my absolute favorite, but if we have an American Gold Eagle bullion coin, so like one of these typical collector's coins you can get, if they're 1 ounce, they would contain 31.1 grams of pure gold. We want to know how many moles of gold are in the coin. All right. So again, we're going to set up the problem the same way, which is, what are we looking for? We're looking for moles of gold. And then what do we know? We know that we have 31.1 grams of gold, and we just have to figure out how to relate these two. So to make sure we do this correctly, we're again going to use dimensional analysis. So we're going to make sure that to put the numbers in correctly, we want the grams of gold to cancel, and we want the moles of gold to be what we go into. And we do have a direct relationship here, grams to moles. That ratio is going to be the atomic mass. So what we need is the atomic mass of gold. So we find gold in the periodic table. It's right here, number 79. And the atomic mass is the number below the symbol, which is 196.97. So that's going to be the atomic mass we use. And to make sure the units work out, we want the grams in the bottom. So it's going to be 196.97 grams of gold per 1 mole. So we want to put the 196.97 in the denominator in this case to make sure that grams divide out, and that gets us to the unit we want, which is mole. So again, in one step we can do this, 0.158 moles. Right? Now in this case, the identity of the substance was important because the fact that it was gold dictated that we had to use this number as the atomic mass. If it was anything else, any other element, we would have to use the atomic mass that's appropriate for that element. So a difference between this problem and the last problem is that when you're converting mass to moles, which is going to be something we're going to do a lot in this course, in this chapter in particular, when you're converting mass to moles, you need to know the identity of the substance, because that's going to then dictate what atomic mass that you use to do that. Every element has a different atomic mass, and so you need to know what the substance is. For Avogadro's number, the relationship is the same for every element, 6.02 times 10 to the 23rd atoms per mole. But for atomic mass, each element has a unique atomic mass that you have to use correctly. So you need to know the identity of the substance. All right, and so that's going to dictate, again, what number we use to relate the mass and the moles. So that was another one-step problem, and then let's do a couple that involve more than one step. So in this problem, I guess it's not so recent anymore, but a few years ago, someone discovered a nanoparticle, meaning basically a huge molecule that's about 1 nanometer in size. When we say nanoparticle, that's kind of what we mean. So it was a huge molecule with a 1.3 nanometer diameter, and it was found to have 37 indium atoms in the structure. So this whole big thing has 37 indium atoms in it. We want to know what is the mass of indium in grams in one of these particles. So in this problem, what we're doing is we're looking for the grams of indium, and our starting point is how many indium atoms we have, which is 37. Now, we don't have a single conversion factor that relates atoms to mass. We have conversion factors that relate number of atoms to number of moles, and we have conversion factors that relate number of moles to number of grams. So in this case, we're going to have to do it in 2 steps, because we don't have a direct conversion from an individual atom to a mass in grams, okay? So what we're going to do then is we're going to do this in 2 steps, and typically the sort of linchpin unit that you want to go through is moles. So when you're doing problems like this, and also when you're doing more advanced problems that we're going to get to later on in this chapter, I always say, when in doubt, convert to moles. So the first thing we're going to do here, we have number of atoms. Let's convert to moles using Avogadro's number. So we can get moles of indium and then atoms of indium on the bottom to divide out. So those divide out, and then again, the way we want to do this is, remember that Avogadro's number tells us that there's 6.02 times 10 to the 23rd atoms in 1 mole. So this time we're going to divide by Avogadro's number to make sure that the number of atoms divides out, and that gets us into moles. Where'd it go? All right, so that divides out. Now that we're in moles of indium, we want to go to grams, and we can again find the relationship to do that. So we're going to use the atomic mass of indium to make sure we put it in correctly. We want grams of indium in the numerator, moles in the denominator. So that moles divide out, and then we want grams in the numerator. So we have to find the atomic mass of IN, indium, which is right here in the middle, 114.82. So we go to the periodic table, find the atomic mass, and the way we want to write that, come back. Oh gosh. Let's see how much of it recovered. That's always the nerve-wracking part of this. I don't know why this program is having trouble the last couple days. I wasn't even trying to erase anything there either. Usually it's when I try to erase a bunch of things that it flakes out, but I was just writing. I know I don't write very well, but that shouldn't crash the program. All right, so let's say we got most of it back. Let's go back where we were. Please tell me it's mostly still there. Good, good. Okay, so we lost some of this. Let me try to put this on one line anyway. Oh gosh, I'm erasing, so don't crash again. So let's try to put this on one line. We're looking for the mass of indium in grams. And as we said, the first step is going to be, we're starting with what we know, which is that we have 37 atoms. And then we can use Avogadro's number to convert to moles. So 1 mole of indium is Avogadro's number of atoms. Sorry, that's atoms, not grams. All right, so those units divide out. Now we have moles, and then as we said, we can use the atomic mass. And what we want to make sure happens is that we want the moles to cancel out and go into grams. And so the way we're going to write this then is 114.82, that's the atomic mass, grams in 1 mole. So moles divide out. It's always grams per mole, so the number that's associated with the atomic mass is going to be along with the units grams, and it's always going to be per 1 mole if we're using atomic mass as a conversion factor. So then what we get is a very tiny number because the mass of 37 atoms is not very large. We get 7.05 times 10 to the minus 21st grams of indium. So we wouldn't be able to measure that accurately, but we can calculate it knowing that there's 37 atoms in the structure. We can convert that to mass using these 2 steps. All right, so that was 2 steps that use basically both concepts that we've learned today. And then one last one here, back to, again, gold, this time a much wealthier individual who has a whole bar of gold, which weighs 12.4 kilograms. That would cost a lot. We want to know how many gold atoms are present in this gold bar. So one thing we want to be careful about here is units, because the mass of this gold bar is in kilograms. Remember that all the relationships involving moles with atomic mass are grams per mole, so we do have to watch out for units in these. I will stress over and over again, when you're doing problems like this, write out the units. If you come for help on a problem and you just write out a bunch of numbers, well, that's often how you confuse yourself, because you don't know which number has which unit attached to it. So always write them out. It might feel like extra work, but it's certainly important to do, especially with these multi-step problems. So this is going to be more than 2 steps. So we're looking for how many gold atoms there are. So it's always good to start with what we're looking for, because then we know when to stop our conversion. And we're trying to find out how many gold atoms are in a 12.4 kilogram bar of gold. All right, so we clearly don't have a relationship that goes from kilograms to number of atoms, but we can do this in a few steps. So we know that if we get to grams, we can use the atomic mass to get to moles. So our first step is going to be converting to grams, 1,000 grams in 1 kilogram. So that conversion factor we should know, because it's just the prefix kilo, which is 1,000. So that gets us into grams. Then the next step, as I said, if we want to find out how many atoms there are, we need to first find out how many moles there are to use Avogadro's number. So we're going to convert into moles. And to make sure we do this right, let's again do dimensional analysis. We want to convert into moles. We want to convert out of grams. So that needs to be in the denominator to cancel out. And that means we're going to use the same atomic mass as before for gold, 196.97, in the denominator per 1 mole. So 196.97 grams per mole, this time inverted to make sure that grams cancel out. So now we have moles. If we want to find number of atoms, then we can use Avogadro's number. So atoms of gold in the numerator, moles in the denominator, so that it cancels out with moles here. And then the definition of the mole is that there's 6.022 times 10 to the 23rd atoms in 1 mole. So moles cancel out. We now have atoms of gold, or number of gold atoms, which is what we're looking for. So we stop there, multiply across, and we get 3.79 times 10 to the 25th atoms, okay? Now, as I said, there's not many times in chemistry when we need to know exactly how many atoms are in a sample of an element or compound, especially if it's a relatively large sample. Like, who cares if there's 3.79 times 10 to the 25th? But that is the definition of a mole, and is one we're going to use regularly, at least at the beginning of this chapter, to introduce the concept. The relationship involving mass, as we'll see, is the one we're going to use a lot more going forward. Yes?
You mean that for multiplication, for 4 times 1,000 times 1 over 196.97 times 0.02?
Yeah, this second line is basically just a continuation. I couldn't fit it all in one line. So it's going to be this times this divided by this times that.
You should have just that. You should have just that. Put all four.
I couldn't fit them in one line. I'm sorry.
At the bottom, not at the top.
I couldn't fit them in one line, so I didn't. And there's gonna, and I mean, this is 4 steps. We're gonna do some problems later on that are like 6 steps. There's no way I'm gonna be able to fit them in one line. So just get used to the fact that if I go to a second line, it's just a continuation of the first. That's how it's going to be written in a lot of these problems. Okay. All right. So let's go on then to talk about another related concept, which is molar mass. So molar mass is perhaps a more general term, but it's usually used for compounds. So we have atomic mass for elements. That comes straight from the periodic table. The molar mass, as the name implies, is the mass of 1 mole of a compound. Now, technically speaking, an atomic mass is still is a molar mass. So it's a molar mass is perhaps a more general term. It's the mass of one mole of any substance. The atomic mass would be the molar mass of an element, where it's just one type of atom in the whole substance. But it's molar mass is more general. It would include any compound that you want to talk about, and the units are still grams per mole, the number of grams of that substance in 1 mole. Okay. Now there are some synonyms and abbreviations we want to be familiar with. So sometimes it will be referred to as molecular weight. Rigorously speaking, we should only use molecular weight for molecular compounds, covalent compounds, but it is going to be used often other times as well. So don't let that throw you off. We're just going to use these interchangeably. It's also sometimes called a formula mass or formula weight. That's used often for ionic compounds, which aren't made up of molecules but have a specified chemical formula nonetheless. So those all kind of mean the same thing. So don't let the terminology fool you. It's really just all these are kind of meaning the same thing, molar mass. And then there's some abbreviations that you'll see as well. Our book doesn't use this, so I think we've mostly phased it out of the homework assignments and tests, but it could still be there in some of the homework assignments, especially. There's this sort of capital script M, which I'm terrible at drawing, but it's like a big M with like kind of in cursive, I guess. I forgot how to write cursive because I haven't done this in 2nd grade, but it's like a capital cursive M basically is one abbreviation that our old textbook used to use, so you might see that sticking around in some of the homework assignments. And then the more common one is MW for molecular weight, which again, we use molecular weight a lot even when we probably shouldn't. It's just probably one of the most common synonyms for molar mass. So if we say the molecular weight of sodium chloride is 58, well, technically that's not correct because sodium chloride is not made up of molecules, but we'll still say that anyway, just kind of to keep the terminology the same. So there's a lot of different terminology, but they all mean the same thing. Now, how do we calculate molar mass? It's actually pretty simple to do. We just have to add together the individual atomic masses in the chemical formula. So to be able to find the molar mass, we have to know the formula of the compound we're dealing with. And we just add together the individual atomic masses to find the molar mass of that compound. Okay? So it's pretty easy to do once you know the chemical formula. All right, so that's how we're going to calculate molar mass, is just take all the individual atomic masses in the chemical formula and add them up. So let's see how we do that. So if you have the simplest amino acid, which is glycine, the chemical formula is C2H5NO2, and we want to know what's the molar mass of this. So to be able to do this, you have to talk a little bit more in detail about these chemical formulas here. So what we're trying to do is find the molar mass of glycine, which is the mass of 1 mole of this compound. And what we have to realize then is that if we have 1 mole of C2H5NO2, what the subscripts in the chemical formula tell us is that the subscript 2 next to carbon means that in 1 mole of this compound we have 2 moles of carbon. So chemical formulas can be interpreted either in terms of individual atoms and molecules. So what you could say is 1 molecule of glycine, C2H5NO2, has 2 carbon atoms in it, but you can also say that 1 mole of glycine has 2 moles of carbon in it, and you can interpret it in terms of moles as well. So 5 moles of hydrogen, because there's a subscript of 5 next to H. 1 mole of nitrogen, there's no subscript next to nitrogen, which means there's just 1 mole in the formula, and then 2 moles of oxygen. So that's another way of interpreting chemical formula in terms of moles, now that we've introduced the concept of a mole. And then if we want to find the molar mass, all we have to do is just add up all 4 of these atomic masses, but we have to account for how many moles of each element are in the formula. We don't just add up the numbers, we have to account for the fact that there's 2 moles of carbon, 5 moles of hydrogen, 1 mole of nitrogen, 2 moles of oxygen. So the molar mass of glycine then becomes, for carbon, we're going to double the atomic mass. And so we go to the periodic table and find the atomic mass of carbon, which is 12.011. And then we're going to also need the atomic mass of hydrogen, which is 1.008. The atomic mass of nitrogen, 14.01. Atomic mass of oxygen, 16. So those are the 4 atomic masses we're going to use, but we have to remember to multiply them by each of the subscripts in the formula to account for how many moles of each of those we have. So for carbon, there's 2 moles in the formula, and the atomic mass of carbon is 12.01. Typically 2 decimal places is fine. So that's what we're going to be our contribution from carbon. For hydrogen, there's 5 moles in the formula, and the atomic mass of hydrogen is 1.01 or 1.008. I guess I went 3 decimal places there, so hope you'll forgive me. And then we're going to add to that on the second line continuing, we have 1 mole of nitrogen, and the atomic mass of nitrogen from the periodic table is 14.01. So that's the contribution from nitrogen. And then we have 2 moles of oxygen with the atomic mass of 16.00 to 2 decimal places. And that's the contribution from oxygen. So we're going to add up all of the atomic masses, remembering to modify the atomic mass by how many moles of each element is in the chemical formula. And so what we get then is 75.07 grams per mole. All right. So what that means is that if we have 1 mole of glycine, the mass of that would be 75.07 grams. Be roughly probably a relatively large handful if you want to put it in terms of those numbers. All right, so any questions on how to calculate the molar mass? All right, so we can do the same thing for ionic compounds. Let's say we have lead-4 sulfate. Now, what I should have told you here is that the symbol for lead is Pb, because that's not one of the first 36, so you wouldn't need to know that. But to do this, we need to get the chemical formula first. So if we give you the name of the compound, in this case we gave you just the name, if you want to be able to find the molar mass, or formula mass as it's often called for ionic compounds, the first thing you need to do is get the correct chemical formula, which we learned how to do in the last couple chapters. So for lead sulfate, we have lead 4+, that's what the 4 means in parentheses, that the charge on the lead cation is 4+, and then sulfate we have to remember is SO4 2-. So if we want to balance these 2 charges and make a neutral ionic compound, again, the simple way to do this is to cross the charges and make them into subscripts. We just have to figure out how many of each we need to balance. So this would give us lead 2 SO4 4. If we want to reduce that to the lowest ratio, which we should do for an ionic compound, it would just be Pb SO4 taken twice. All right, so this is the correct formula for lead 4 sulfate, which we need to be able to calculate the molar mass. And now to do that, to find the molar mass of lead sulfate, what we're going to do is just add together the atomic masses. So we have 1 lead, 1 Pb, and the atomic mass of Pb is 207.2. So we have 1 times 207.2 grams per mole is the contribution from lead. And then we have to remember that when we have a formula like this, SO4 taken twice, that means everything that's in the parentheses is modified by the subscript that's outside the parentheses. So we have 2 total sulfurs. 2 sulfurs in the formula. SO4 taken twice means there's 2 total sulfurs, and the atomic mass of sulfur is 32.07. And then how many oxygens do we have? Somebody said it. It's 8 because there's 4 per sulfate, but there's 2 sulfates. So 2 times 4 is 8 for oxygen. And as we saw in the last problem, the atomic mass of oxygen is 16. So we have lead, sulfur, oxygen, 1 lead, 2 sulfurs, 8 oxygens. We're going to add up all those atomic masses, and we get a number that's 399.34, assuming I did things correctly. Yes, thank you. All right, so it's going to be plus 8 times 16. And so we get 399.34 is the correct answer for this one, grams per mole. Okay, so that's how we would do for an ionic compound. We have to, again, remember we have to get the formula correct first, and then if you have polyatomic ions, make sure you correctly count the number of each element, each atom that's in the formula. Okay, so that's how we calculate molar mass. Let's see how we use it in context. So we're going to use molar mass very much the same way that we use atomic mass, just as a relationship between mass and moles, this time for a compound instead of for a single element. So I mentioned to you that my favorite element is iridium. So here's an iridium compound that one of my students prepared in my research lab, and it generates red light. As you can see, it's glowing red. It has a lot of other things besides iridium, though, and the whole molar mass of this compound is 774.94 grams per mole. So it's a relatively large molecule. It has 1 iridium in it, but it has a bunch of other carbon, nitrogen, probably sulfur in this one as well. No, this one does not have sulfur. Carbon, hydrogen, nitrogen, and iridium. So I'm not giving you the exact formula, but the molar mass is 7074.94. And we want to know how many molecules of this compound are in a 1 gram sample. All right. Not particularly useful to know how many molecules there are, but we can do that calculation. So just like we did before, we're going to write down what we're looking for, which is number of molecules. And we're going to write down what we're starting with, which is a 1 gram sample of the compound. Now, we don't know the exact chemical formula because I didn't give it to you, so I'll just abbreviate it as iridium in brackets. It's an iridium compound, but it has other things too. It's not pure iridium. And then what we're going to do is we're going to use the given molar mass, 774.94, to convert grams into moles. Because again, if we want to find the number of atoms or number of molecules, we have to go through moles first to be able to use Avogadro's number. So the first thing we're going to do is we're going to convert grams to moles. We want grams to cancel out. So that's going to be in the denominator, and then that's going to be per mole of the compound. And this number here, 774.94, is going to go in the denominator. 774.94 grams of the compound per 1 mole. So that allows grams to divide out. And then the last step, which I read out of room because I wrote too big, is going to be we want to go from moles to number of molecules. So we're looking for how many molecules of this compound we have. And just like we can use Avogadro's number to figure out how many atoms are in a sample of an element, we can also use Avogadro's number to figure out how many molecules are in 1 mole of a compound. All right? So we're going to use Avogadro's number. We want moles to cancel out, and we want molecules to be in the numerator. So it's going to be 6.022 times 10 to the 23rd molecules of this compound in 1 mole. That allows moles to divide out. And we get 7.77 times 10 to the 20th molecules. All right, so really almost identical to the calculations we did before with single elements. This time we're doing it for a compound, and the only difference is that for a compound, the relationship between mass and moles is just the molar mass of the whole compound. And because it's a covalent compound, we're going to use, in this case, Avogadro's number is going to tell us how many molecules there are, not how many atoms there are. All right, so that one tells us how to use molar mass. Any questions on molar mass before I move on? All right, so the last thing we're going to cover today is mass percent, which we've already covered in some context. So if you remember way back, one of the very first things we did in this class was talk about the law of definite composition and how we can define the composition of a chemical compound in terms of the mass percents of its elements. We talked about that a long time ago. So just as a review, the mass percent of an element in a compound is the mass of that element, which I'll call A, divided by the mass of the compound multiplied by 100 to make it a percent. So that's the definition of mass percent. And before, what we did in chapter 1 was we would either just give you the masses and have you calculate the mass percent, or we would give you the mass percent and have you do some simple conversion with it. But now what we're going to talk about today is the relationship between chemical formula and mass percent, which involves using molar masses, what we've been talking about the whole time today. So now that we know these concepts, if I give you any chemical formula, I could ask you and you could figure out what would be the mass percent of this element in that chemical compound. So the way that we do this is whenever we're doing problems like this that deal with composition, we're going to assume some convenient amount of that substance, and what we're going to do for this is we're going to assume 1 mole of the compound. All right? Because remember, the mass percent is going to be representative of any amount of that compound we had. Whether we had one speck of the compound or a huge pile of it, the mass percent is going to be the same. So we're going to assume that we have 1 mole of compound when we calculate it. And the way that works then is if we want to find the mass percent, it's going to be the mass of the element that we're looking for. In this case, I'll call it A, again, in 1 mole of the compound, divided by, and then we want to divide that by the mass of compound in 1 mole. What's the mass of a compound in 1 mole of that substance? What's that called? We just introduced it today. Molar mass, right? So if we're assuming 1 mole of compound, the mass of the compound is just the molar mass of the compound. All right? So that's going to be our denominator. And then we multiply that whole ratio by 100. All right, so if we're assuming 1 mole of compound, the mass of the whole compound is just the molar mass, and then we just have to figure out how much of that molar mass comes from that specific element and divide the two. Okay, so this is best learned with an example. So if we want to go back to the compound glycine that we calculated the molar mass for earlier, we want to know what is the mass percent of carbon in glycine. Okay, so that would be a typical problem we'd have to do. So what we're going to do in this case is we're going to, again, assume 1 mole of compound, as we said before. We assume 1 mole of C2H5NO2. And as we already calculated a few slides ago, the mass of 1 mole of this compound, in other words, the molar mass, is 75.07 grams. So that's how much mass we have in 1 mole of the compound. And if we want to figure out the mass percent of carbon in the compound, we need to figure out what portion of this 75.0 grams is made up of carbon. Okay, so the mass of carbon in 1 mole, what we have to remember is that we have 2 moles of carbon in 1 mole of the compound because the subscript 2 next to carbon. So we have 2 moles of carbon in 1 mole of the compound, and then we're going to use the atomic mass of carbon to figure out what's the mass in grams of 2 moles of carbon. So if we go to the periodic table to remind ourselves, the atomic mass of carbon is 12.011. So if we have 2 moles of carbon, we want to figure out the mass of that 2 moles. We want moles to cancel, grams to be left, and so we're going to use the atomic mass, 12.01 grams in 1 mole. So moles cancel out, and this tells us that 2 moles of carbon has a 24.02 gram mass. And so what that means is that out of the 75.07 grams, which represents the mass of 1 mole of glycine, 24.02 grams of that is carbon, and then to figure out the percentage of carbon, we just have to divide the 2 and multiply by 100. So the mass percent of carbon is 24.02 grams of carbon, which is the mass of carbon in 1 mole, divided by 75.07 grams of the compound, which is, again, the mass of 1 mole. So both of these represent the mass in 1 mole. And then we multiply that by 100, and we get a percentage of 32.00%. All right? So the mass percent of carbon in this compound is 32%. If we did the same thing for the other 3 elements, hydrogen, nitrogen, and oxygen, we could get their percentages, and they should add up to 100 if we did everything right. So what we're going to cover next time is some more relationships involving the moles, and we're going to talk about how to use that in studying chemical reactions, as well as how to work backwards. So we now know how to go from chemical formula to mass percent. Next time we're going to show you how to go from mass percent back to chemical formula. We can go both ways. So we'll see that all next time, and I'll see you guys on Wednesday.